I feel the need for speed. That worked well for Maverick and Top Gun, but when it comes to hydronic systems, too much speed or not enough can create some serious problems. A few years ago, I walked into a finger pointing contest inside a boiler room. The maintenance staff replaced air vents, changed circulators, flushed part of the system, and spent countless hours bleeding radiators and getting water, no air. The problems? Some radiators stay cold, the piping was noisy, air problems seemed to never go away, the boiler short cycled constantly, the pump manufacturer blamed the boiler manufacturer, the boiler rep blamed the pump manufacturer, the maintenance staff blamed both of them. But the real problem was something no one checked: water velocity. This is Ray Wohlfarth, Boiler Room Detective. Looking for more info on hydronic heating systems? Check out my books, Lessons Learned Replacing Old Hydronic Boilers and Lessons Learned Troubleshooting Hydronic Heat. Welcome, detectives. Today we're going to learn why water velocity is one of the most important and most overlooked parts of the hydronic heating system. What is water velocity? Water velocity is simply how fast water moves through piping. We usually measure it in feet per second, or FPS. Most hydronic systems are designed to operate somewhere between 2 and 4 feet per second. Think of it like driving a car. Too slow and the traffic backs up, too fast and things start breaking. Hydronic systems work the same way. The goal is finding that sweet spot. Why does velocity matter? Water velocity affects heat transfer, air removal, system noise, pump energy consumption, equipment life, and overall system performance. Get the velocity right, and the system runs quietly and efficiently for decades. Get it wrong, and you'll be chasing problems for years. What happens when the velocity is too slow? When water velocity drops below 2 feet per second, several problems begin showing up. Poor heat distribution. The water may be cool before it reaches the furthest radiators. The result? The Goldilocks effect. Some areas are hot, some are cool, and some are just right. The second item is reduced heat output. When flow slows, the system simply can't move enough BTUs where they need to go. Another consideration is boiler damage. Low velocity creates wide temperature differences, which can cause thermal shock, ruining the boiler. Most hydronic boilers are designed for a 20 to 30 degree temperature differential. When velocity is too low, dirt and sediment can settle in piping, coils, and heat exchangers instead of making their way to strainers and separators. Air problems. This is the big one. Air bubbles are lighter than water. When water moves too slowly, the bubbles can become trapped in the system. This can lead to cooled radiators, noisy piping, circulator problems, corrosion, reduced heat transfer. What happens when the velocity is too fast? Most technicians assume more flow is always better. Not necessarily. Once velocity climbs above roughly 4 to 6 feet per second, new problems can appear. Noise. High velocity water sounds like water rushing through the pipes, or a whooshing or whistling sound. Erosion. Water can become surprisingly destructive when it moves too fast. Over time, high velocity can wear away piping, fittings, elbows, and valve components. This can shorten equipment life and increase maintenance costs. Higher energy costs. Moving water faster requires more pumping power. The circulator works harder, electric consumption goes up, operating costs increase. High velocity can create more turbulence. The turbulence can break larger air pockets into tiny microbubbles. These microbubbles are more difficult to remove. While slow velocity traps air, excess velocity can create new air management challenges. The sweet spot. For most hydronic systems, we're looking for balance. We want water moving fast enough to deliver heat, carry dirt to separators and strainers, and move air bubbles to air eliminators. But we want it slow enough to prevent erosion, reduce noise, minimize pressure drop, and protect equipment. That's why most designers aim for approximately 2 to 4 feet per second. All that goes out the window when zone valves are added. As zone valves close, the pump may continue producing the same pressure. That pressure now gets pushed through fewer open zones. This results in higher flow rates and increased velocities in the remaining zones. This leads to more noise, more wear, more complaints. That's one reason variable speed ECM circulators have become so popular. As zones close, the circulator automatically slows down and helps maintain a proper flow and pressure through the system. In many cases, an ECM circulator can solve problems that technicians have been chasing for years. The next time you walk into a building and find cold radiators, noisy piping, air problems, short cycling, uneven heating, don't just blame the boiler, don't blame the pump. Ask yourself one simple question: how fast is the water going? Because sometimes the difference between a system that works beautifully and one that constantly creates problems is only a few feet per second. This is Ray Wohlfarth, Boiler Room Detective. I'd love to hear about some of your strange hydronic problems you've discovered in the field. Leave a comment below. If you enjoyed the video, please subscribe and share. I'll see you on the next case.